Hello everyone, this is Mr. Chiu. I hope that you are having a good start for the day. And today I'll focus on topic 4.2, which is on general waves. Now this is a rather easy topic, but there's some important points that you need to be very clear of, so that you don't get confused in the later part of topic 4, because it builds on these fundamental ideas. So let's start off with some basic concepts of what wave is. You need to know that wave is a mechanism of energy transfer without a transfer or detransfer of the medium itself. What do I mean by this? It means that, say for example, as I'm talking to you in real life, say for example, the voice, the sound energy transfers from me to you, but the air doesn't get from me to you. So the wind doesn't come. Of course, if I speak loud enough, the air will come to you. But the thing is, the air doesn't move, but the sound energy gets transmitted. Or if I were to dip my finger into the water, the waves travel outwards from the point where I touch the water, but the water doesn't run away. So the medium, which is the water itself, doesn't move away, but the wave transfers the energy. So this is what wave is, if you are asked a definition of what wave is. There are two kinds of wave: longitudinal and transverse wave. You have learned this before. So longitudinal wave are waves where the particles vibrate parallel to the wave motion. So I want to see the key phrase or the key idea that the particles vibrate parallel to wave motion. So even though some of you or most of you remember the word parallel for longitudinal wave, but you need to know what is parallel to what. Most of the times when I ask students to define, they missed out this or this. The parallel is always there, or the perpendicular is there. So transverse wave, this is perpendicular to this. Not much of a difference. You need to know how to quote examples. So for longitudinal wave, the only example that you need to know is sound wave. But of course, one very interesting question that I always ask students is, why is sound wave a longitudinal wave? Why is it that sound wave cannot be a transverse wave? We'll leave that for discussion in the future when I see you face to face. Think about this. Why can't sound waves be transverse waves? Why must it be a longitudinal wave? Transverse wave, EM waves, waves on a string, waves on the water, on the surface of the water, even though waves underwater can be longitudinal. So these are examples of longitudinal and transverse. I'm going to go through two ways of describing waves to you, and I will bypass the very basic stuff of what's the amplitude, wavelength, period, and sort. I'll jump straight into the more difficult parts of waves that you may face problems with. So I will assume that you know what is meant by amplitude, wavelength, period, frequency, and wave speed. These are technical definitions that you have been acquainted with in Sec 3 or 4, and they are rather basic ideas. So I will not go through too much. They are in your notes. What I will want to go through are things that are more difficult conceptually. So you need to know this is amplitude, wavelength, period, frequency, wave speed. This is F lambda, this is 1 upon T. So these are some basic stuff that you need to know. The more difficult things that usually students have trouble with is the XT graph and the XD graph, or DX graph, depending on what they're talking about. So let's begin with XT graph. So if you look at the XT graph, I have this wave over here, and if I give you this as time t, you need to know how to get a period. Now, this is rather basic. We'll come to the more difficult things soon. So in this case, it is best for students, if you're asked to find period, it is best for you to do it this way. I recommend that you write t equals to count how many waves is that. So in this case, it's 1 1/4 of a period. Why period and not wavelength? Because the axis is time. So it doesn't make sense for you to have a time axis and then wavelength. So the thing is, you transfer this over 4 upon 5 t. So in a nutshell, you always begin with what you have. Don't bother thinking t divided by what, because it will naturally work out if you follow this step. Just write t, count the number of waves equals to how many period, and then transfer over. You naturally get the answer if you do it correctly, if you follow this properly. Now what is more difficult is this. There are 4 points over here, A, B, C, and D. Which is or are the points that are moving up, assuming that this is a transverse wave. Transverse waves are easier to understand when we apply this to transverse wave. I'll explain why when we go to longitudinal wave. So for transverse wave, as the wave moves, the particle moves up and down. In this case, it moves up and down. So which is or are the points that moves up? Okay, how do you know which point is moving up? The how is important, the method is important, because the method can be replicated. The answer may differ depending on the waveform. So the how is important. Let's say, for example, if I'm telling you that I'm moving left and right, and I ask you to tell me at this moment, am I moving left or right? There's no way for you to tell unless I tell you that the next point of time, the key is the next point of time. If I'm here, do you agree that you can deduce, therefore, that at this point, I'm moving this way? So the key over here is at the next point of time, where is the position of the particle? So for this one, at the next point of time, time can only go towards the right. Kind of weird to say that time goes towards the right, but in this axis, time is increasing towards the right. So at the next point of time is here, next point of time is here, next point of time here, next point of time is here. So therefore, for this, it moves down, down, up, up. So that's why A, B are the points moving down, C, D are the points moving up. Now, second question. Which of the points are the ones that are slowing down? Which is or are the points that are speeding up? What do you think? Remember that I mentioned in kinematics that negative acceleration doesn't mean deceleration. The key is if acceleration and velocity are in the opposite direction, it will slow down. If they're in the same direction, you speed up. In case you don't remember this case where you throw something up, the acceleration is always down because the acceleration of free fall is always down, the earth is there. So the velocity at point 1, point 2, point 3, this is pointing up. Different direction, velocities and acceleration, so it slows down. Over here, the velocity is downwards. Same direction, speed up. Same direction, speed up. So it doesn't matter whether it's negative or positive. So long as it's the same direction as the velocity is the same as the acceleration, same direction, it will speed up. If it is in the opposite direction, then it will slow down. So this is making reference to what you have already know. Just a quick refresher. Now applying it to a new context. Let's take a look. Remember the SHM, the acceleration always point towards the center of the motion. So in this case, the center of motion is here, the V is here, the A is here. The V is here, the A is here. The V is here, the A is here. The V is here, the A always points towards the center of the motion. That's 4.1. So this will speed up because it's in the same direction. Speed up, slow down, slow down. That's another way of looking at this. You just look at a pendulum. Whenever it moves towards the center, it will speed up. Whenever it moves away, it will slow down. So that's a more layman way of looking at this one. Observation. That's one way of understanding and coming up with rules of the nature from observation. But I prefer that if you can actually explicitly make it connecting the observation or the outcome to certain fundamental ideas, that will be much better in case you're asked to explain. So to summarize, how do you know whether it's speeding up or slowing down? Look at the direction of acceleration and velocities. Okay, now I'd like to go through this other graph, which is I think really interesting. The way to go about this is about the same. So if I got A, B, C, and D, if I were to have a wave that moves this way, and you need to know this because if I ask you to find the direction of motion of the wave of this point at that point of time, there's no information about time. It's dx. There's no time information. It's just like taking a photo of a tree. How do you know whether the tree is moving towards the right or left at that moment? There's no way to know unless you have the picture at the next moment. So for this one, you need the direction of the wave motion. So the wave moves towards the right. So at the next point of time, the wave profile looks like this. Remember back to the original idea about wave. It is a mechanism of energy transfer without the transfer of medium. So what does it mean in this context? That means that this point doesn't move with the wave. As the wave moves past, it oscillates up and down. Therefore, A moves up to the new position. Remember, the position at the next point of time tells you the velocity. So this one moves up, down, down. Needless to say, remember, whenever point moves towards the equilibrium, it will speed up, it will speed up. Slow down, slow down. Alright, so this is how you look at using a xt graph or xd graph, the direction of motion, and also whether it's accelerating or decelerating. Cool? Now, one last thing that I want to go through with you for longitudinal wave is this. Remember that for longitudinal wave, one of the very important defining feature of, say, sound wave is that it has a R and a C. So what are the R and C? Rarefaction and compression. So how do you know the positions of rarefaction and compression from a graph that looks like this? Now you can't tell from this graph just by this. Say for example, let's make our life a little bit more difficult. Usually plus points towards the right. Let's say towards the left is positive. Now what do I mean by this? The problem with longitudinal wave is that as the wave moves past, the particles move this way. Whereas we have to represent the wave displacement, the particle's displacement by this. So the dilemma for longitudinal wave is that, well, the particle is moving this way, not this way. We have to represent it as a wave that looks like this. So it is very, very misleading sometimes for students to think that the wave, how do you connect like a particle motion like this to this? So that's why we need this. So what do we mean? If you have, say, for example, this point, a particle at this point has positive displacement. So it means that by the convention, the particle over here is displaced towards the right. The particle over here, it is displaced negatively. Probably I shall take this away in case it causes confusion. The particle over here is displaced negatively. So it gets displaced by convention towards the right. Now can you see now that this point is the point where particles move away? So this is the rarefaction. I think by deduction, you'll be able to tell that this is compression. Let's check. This point over here is positively displaced, so it goes here. This point over here is negatively displaced, so it goes here. So that's the compression, and therefore this will be rarefaction and so on and so forth. So in summary, the x-intercept of the graph is always the compression or rarefaction. As to whether it is compression or rarefaction, you need to look at this, determine the movement of the particles to the left and the right of the point. And take note, whenever you want to find the amplitude of the wave motion, say for example, in case you're given something like this, and like this, like this. So this is the compression, this is the rarefaction. These particles move away. Now, how do you know which particle is the particle that undergoes the maximum displacement? That means the particle at the amplitude. Very easy. Like this, you look at compression, rarefaction. The point between compression and rarefaction is the point that has the maximum displacement, which is the amplitude. So if this is the rarefaction, this is the compression. 1, 2, 3. The point at the center is the one going through the amplitude. So you just need to know the original position of the particle, then you find what's the displacement of it away from the original position. That's how you find the compression, rarefaction, and the particle which has the maximum displacement from its original position. Alright, so that's more or less it for 4.2. Really simple, fundamental, but important topic, which will lead on to 4.3, 4.4, and then 4.5. Alright, I wish you a very meaningful and effective and efficient use of time for HBL Day, and see you tomorrow.